Okay, so autonomous means that this doesn't explicitly depend on time. Yeah, A is a constant. If A was a function of time, so you could make A a function of time, then it would be non-autonomous. Homogeneous means that when you take x and set it to 0, the right-hand side is 0. So it means that x equal to 0 is an equilibrium. So this is homogeneous. And now we're going to talk about non-homogeneous. Non-homogeneous, and remember we're talking about linear models. What makes this linear is that on the right-hand side we have a linear expression. A general linear expression, dx dt, consists of a constant and a term dependent on x. And so we're going to write down a plus, and I'm going to use y here instead of x. I'm just going to work with the variable y. So that is a general linear, a non-homogeneous equation. It's still autonomous because neither a nor c depend explicitly on time. If I wanted to make this periodic with regard to time, what kind of functions could I use? What functions do you know are periodic over time? Sine and cosine. Okay, so I put in sine and cosine. But these are going to be constants. Now, this equation describes the simplest case of what are called mixing models. And mixing models come about when you think, when you've got some kind of compartment Y, and there flows into this compartment and flows out of this compartment. Now, in a mixing model, the flow into the compartment is usually considered a constant. It's determined by something external, and it's just flowing in. So it could be something flowing in at a rate A. And out of here, there's a flow. Most mixing models assume that the flow out is proportional to what's in here. So the flow out would be B times Y, where B is the rate per unit concentration. This equation would be written as dy dt. The rate of change of Y depends on the flow rate in. So if the measurements of this are density or concentration, this would be the amount flowing in would be, if this is, for example, mass, then this would be mass per unit second flowing in. Or if this is a volume, cubic feet, this could be cubic feet per unit second. This could be a reservoir, and water could be flowing in. And if this is a dam, maybe this is the water coming in upstream, then you might release water from that dam at a rate that's proportional to how much is in the dam, or at a fixed rate. If this is a constant, then we'd have to have a different term. But if we're assuming that it's proportional to what's in there, then this would be minus b times y. So here you see this is the same as this, where c is minus b. So we have these models that are sometimes called compartment models. Now I'm going to talk about a slightly more complicated compartment model. So this material is all in section 6.3. And we have a number of examples that I'm going to talk about in section 6.3, but I want to go to a more general problem now, just to set it up for you, so you can see, and that is a compartment model that's often used in medical sciences or in drug therapy, is if you have a drip into your bloodstream, then you have a concentration of the drug going around in your body. And very often that drug may be targeted to go to some particular organ. For example, it may be a painkiller, an opioid or something that's targeted to go to your brain. So you have this blood-brain barrier, and you have these drug molecules that, in the drip, these molecules are mixed into your blood, circulates the heart, it goes everywhere, and there's a concentration in your blood. And then the rate at which it goes to your brain depends on that concentration, and these molecules go across the membrane that separates the capillaries in the bloodstream from the brain. And so this is called the blood-brain barrier because only certain kinds of molecules can go across, smaller ones. Typically, it doesn't allow bigger ones, and that's kind of a defense against bacterial infections in your blood. Bacteria are relatively big. You know, they're whole single-cell organisms, and so the blood-brain barrier is trying to prevent these bacteria from getting into your brain. It doesn't always work. For example, in Lyme disease, there's a very small bacterium called a spirochete, and it can drill through membranes. And so it actually gets into your brain by drilling through the membrane. It's got like a corkscrew shape, and it goes through that way. So in that case, you might have two compartments, one that you call X and one that you call Y. And this could be the blood, and this could be the brain. And actually, I'm going to go one step further, and I'm going to have three compartments. And I'm going to call this a large muscle, like your gluteal muscle, so that sometimes you get an injection into your butt. And you might ask, why? Is the doctor just a sadist? And he has the blood, and he has the brain. And so your fifth homework assignment is actually going to be investigating this question of, is the doctor a sadist? And why would they want to inject the drug into a large muscle, maybe on top of your arm, which will then slowly perfuse into the blood as the blood circulates, which will then head to the brain. So if you've got morphine, for example, you can get a morphine injection or you can get a drip. If you get an injection, then what happens is if at time 0 you get an injection, you can say x at time 0 is equal to a. So if this is a muscle that has no morphine in it and you get an injection, then at that point in time, which we'll call time 0, your muscle now contains a certain amount of morphine. This morphine then goes into the blood at a certain rate, proportional to the concentration in the muscle. So proportional to, let's say, a times x. Then it circulates around in the blood, and it goes into your brain. And it goes there at a rate proportional to the concentration in your blood. So you can see now why linear models are good for this. Because the rate at which molecules will go from one compartment to another, diffusing across barriers, is going to be proportional to the concentration. Now, it may be that the doctor could put up a drip and inject every so often, at a very slow rate, a small drop of the drug into you, drip, 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 drip. And you can think of this as a continuous rate of putting drug directly into the blood. So there are two different strategies. Here, Y of 0 would start out at 0, and Z of 0 would start out at 0. So you've got no morphine in your system. And then you get an injection, and you start out with a certain level of morphine in the muscle. Or you may not get an injection, and you don't have to consider this. What we're assuming is that concentration doesn't go back from Y into X, and that is because we assume that morphine molecules are highly directed in the way they transport it to different places in the body. Now, that may not be entirely realistic. There may be some leakage out of this compartment Y into other organs, but we're assuming that it mainly just goes across the blood-brain barrier because there's certain carrier molecules there that transport it over. And then, if you have a drip, slowly you're adding to the blood, so the blood may initially get from the molecules or the concentration in the muscle going to the blood. You can introduce it another way through a drip. So you can think of the muscle or the drip as two ways of introducing, over time, morphine into the blood, which then over time gets into the brain. And so I'll talk a little bit about this towards the end of this, but you can set up a model over here where the XDT leaks out. So A is minus 1 over 8. And then, in fact, here I've called CB. So I'll call this B over here, and I'll call this C. B is the rate at which you introduce through a drip. C is also minus 1 over 8. So this is the rate at which a unit of concentration, and if this is per hour, it's like 1/8 of the morphine in your blood per hour will shift over into your brain. That's what that 1/8 means. So these are linear models. But we're going to just start off here talking about the simplest of these models, and that is a scalar model. This model is a three-dimensional model. A scalar model is a one-dimensional model. And for example, one-dimensional models have been used to model the clearance of HIV particles in an individual's blood from a production site in lymphatic tissue. I'm not going to go through this example in any detail. This is example 6.3 in your textbook, example 1, section 6.3, and you can take a look at it. I will talk a little more about, and there's another example which you can look at. I'll come to what we call the general solution to this equation. And we're going to talk about the general solution to this equation. So we're going to talk about the case where this is minus b times y. Now, you can integrate this equation from some initial condition in the same way that we integrated. Excuse me, at the back there, I said that I prefer it if you watch the board rather than your laptop. Same over there. Thanks. I mean, you may be watching the talk, you may be watching something else. I'm not going to ask you. I guess you were watching the talk. But this way, I know whether you're watching my talk or not. Okay, so I can integrate this. And in the textbook, you'll see some examples integrated. For example, this one, determining an infusion rate. Example 2, you'll see it integrated where A and B have specific values. And from that, you can infer, or you can integrate with parameters rather than specific numbers, and you can show that the general solution to this equation is y of t equals A over B minus C e to the minus bt. This capital C is an arbitrary constant. An arbitrary constant. If I specify an initial condition, then I can determine what C is. How do I determine what C is? How can I get an equation to find out what C is? If I know that y at time 0 is this given number y0, then I can say y at time 0 equals ab minus c. Now e to the minus 0 is 1, so that's equal to y0. So that means if I take c to the other side, I get c is equal to ab minus y0. So swap. I take c to this side, and I take y0 to that side. And so this arbitrary constant is determined by the initial condition. So if I don't specify an initial condition, and I just integrate this, whenever you integrate something, you remember from calculus, you get an arbitrary constant. When you integrate a differential equation, what determines the arbitrary constant, once you integrate your equation, is some point along the solution. You fix the solution from a family of solutions that you get with the arbitrary constant. Okay? So what's an easy way to check that that in fact is true? I mean, does it look reasonable? Does it look like that solution is reasonable? How would you check if it is a solution? Any ideas? Yeah? Or you differentiate it? Yeah, you differentiate it. That's right. So let's do that. So let's say dy dt. So I'm looking at the solution. Now, what's d by dt of a constant? 0. Minus c times, and now differentiate e to the minus bt. So what's the derivative of that? So it's going to be plus, it's going to be minus times a minus is a plus, b e to the minus bt. So if I differentiate this, then that's what I get. Now, in order to show that this thing over here is the same as this over here, you just have to use your mathematical insight, your mathematical mind. Now, everybody's mathematical mind varies from brilliant to, I guess, average. And just like some people are great musicians and some people are not. But you can learn tricks. So it looks like we need to have an A in there. So why don't I add and subtract an A? Add and subtract an A. But it looks like we've got an extra B here. So if I put an extra B over here and divide by B, I'm where I want to be. No pun intended. And I can take out a B here. So that's minus B into A over B minus C e to the minus bt. So that's equal to A minus B. Now this thing over here is just y of t. So there we've got that if this is the solution and I differentiate it, I get to the original equation. So in the same way that this implies that. So this equation over here implies this. However, it's not clear exactly what C is, so we have to express C in these terms. So another way of writing this is I can take y of t over there, and that's equal to a over b, and then minus C. Now what is C equal to? C equals to a over b minus y0, e to the minus bt. So I can also write it in this term if I want to write it explicitly in terms of y0. And I can leave it in this form, or I can organize it in a slightly different form. It's probably best just to leave it in that form. So in other words, the differential equation up here for this initial condition means that the solution can be written down like that. So that's a little more complicated than the homogeneous exponential. But if you want to write down the solution, it's not too complicated, and you can just keep it in mind, and you can have it somewhere to look up if you want to reference it. Okay. Yeah. Well, C is not given. C is not. So if I say to you, what's the solution to this equation, then A is given, B is given, and y0 is given, but C is not given. Now, when I do this, I say that the solution to this equation can be written down in the simplest form like this, if I don't know what this is. If I am given this, then I can go through this exercise and say C is actually A over B minus y0. And so if I am given A, B, and y0, then I can write the solution down like this. The reason why it's written down in textbooks like this is they're just looking at this equation without specifying any initial condition. Specifying initial condition is less general. It makes it a special problem. It's called an initial value problem. This is just a general differential equation, and it defines a family of solutions for particular A's and B's, because it's like when you differentiate something, the derivative of a constant is 0, so when you integrate a constant, you get a linear function, and so, but that linear function, you can vary its height. It's just the slope that's determined. And in order to get a particular line of that slope, you have to pin it down by looking at its intercept. So if I've got a bunch of lines, the derivatives are all the same because the derivatives of the slope. But which of the lines am I really interested in? Well, I have to specify what its intercept is, then I can get the particular line. So it's like this solution gives me a family of curves. I say, which of these curves am I interested in? It's the one that's pinned down by the initial condition. Okay? So let's apply this immediately to something that we came across in the last lecture, and that's the von Bertalanffy growth equation. Now, von Bertalanffy said that an organism grows in its length, dl dt, at a rate that's determined by two parameters, k and L subscript infinity. And the rate at which it grows is how much further does it have to go to get to L sub infinity. So L sub infinity is the maximum rate. So is the maximum size. Its current size tells you how close it is to its maximum size. So this is your variable telling you what is its current length. The closer it gets to its maximum size, the slower it grows. This parameter k just tells you intrinsically how much potential this organism has to grow. So this is kind of like a rule in biology. Now, physics has rules that we call laws, like Newton's law. There's Newton's law of motion, and in this section there's something I don't deal with, but it's called Newton's law of cooling. And Newton's law of cooling says that the amount you're going to cool is proportional to how far you are to the ambient temperature. So if you're above it, or if you're below it, you can warm up compared to the ambient temperature, exchanging heat to some power. Von Bertalanffy's law is not a law because it's biology, and biology things don't behave like in physics, where in physics you have these inanimate objects, matter, and they seem to obey laws very well. In biology there's a huge amount of variability, the entity is very complex, and so what we call rules, we call them rules rather than laws because they kind of apply, and it's nice to have something general. And von Bertalanffy was saying, okay, here's a rule that I'm going to propose, and we'll see how well it works. And so what biologists would then do is they would say, okay, here's a bunch of organisms. Here's a bunch of different kinds of fish, a bunch of different trees, some kind of birds. And they would have a look, do these growth laws apply? For each one of these, can we look at some linear measure, whether it's a height or a length? So this could be a height, could also be a width. And over time, you start out at a particular point, and here you can say we start out, L0 is going to be specified, and then we get some data. And now we're going to write down the general solution to this equation. So let's see if we can do this. This is KL infinity minus KL. So if we look above, this is like our constant A, and this is like our constant B.